Okay, everybody, welcome back. Hope everyone's doing okay. Just a quick announcement. Don't forget your next exam. Due late this evening, same as the others, time-wise. Give yourself plenty of time. Any questions concerning those chapters or anything else? Any questions at all? Yeah, if no questions, I will continue, which I believe we're in chapter 10. No questions? Okay. All right, then. Well, let me share the screen. And we're going to jump into chapter 10, which deals with chemical reactions. Now I did introduce you to one type of chemical reaction, and that was the acid-base reaction or the neutralization reaction. Okay. I may have also mentioned another one, a combustion reaction. Okay. The point of this is that of all the reactions that are out there, there's only 6 different types of reactions of which we're going to learn. Okay. We're also going to learn how to balance these reactions. And what we mean by balancing is that when in any chemical reaction, based on the law of conservation of matter, that whatever quantity of material I start off with as reactants, the same quantity of material will be obtained at the end of the reaction in products. Okay, that is the conservation of matter law, because matter, as we know, is neither created or destroyed and basically just moved around. Okay, so let's say, for example, that you are doing a reaction and you start off with, let's say 5 grams of reactants, okay? And let's break it up this way. We got A plus B reacting to give us, let's say, C. Well, maybe we have 2 grams of A and maybe 3 grams of B. Well, once the reaction is complete, okay, and all the A and B has been converted to C, we should end up with a total of 5 grams of C. And that's what we mean about the conservation of matter. The total mass would be the same before and after. Now, in reality, just because the conditions are not 100%, that's not always the case. We don't really get the total amount. We lose material along the way. Another way to look at it is whatever number of atoms that we start off as on the reactant side, we will obtain the same number on the product side. So in this example here, to say if I have it's an arbitrary number. If I start off with 254 carbon atoms as a reactant, then I should end up with 254 carbon atoms as products. Now they're going to be different, okay? They're being different type of carbon atoms, but they'll still carbon, just in a different form. Okay. Now, once we know that material, that information, we have what's called a balanced chemical reaction. And the way we balance them is we're going to put coefficients in front of the reaction. So let's go back to the general reaction. We got A plus B reacting to give us, maybe this time we got 2 different products, right? Whatever A, B, C, and D is. But maybe we needed 2 molecules of A. Okay, I'm not talking about grams. I can use grams or molecules, but let's talk about molecules. If I started off with 2 molecules of A, maybe that required 3 molecules of B for this reaction to proceed. And when everything was done, we may have ended up with 2 molecules of C and maybe just 1 molecule of D. So that coefficient That number in front is the coefficient, and we can input that number, change this number to any number that we need, such that the quantities, we add enough of those coefficients so that the quantities of atoms are equal both as the reactant side and the product side. And hence we use the term balance. Those coefficients are going to be an important part of our future calculations. So we're going to introduce the chemical reactions, and then we're going to talk about balancing them, okay, and learn to balance them. And once we learn that, the next step, not in this chapter, but the subsequent chapters, we're going to use that coefficient, that information, to eventually, for example, let's say we need, for whatever reason, 100 grams of D, okay? Well, the question may be, well, given that we have enough of A, how many grams of B do we need to produce 100 grams of C? And we're going to go through a series of conversions of the grams into a unit that we call moles, okay? Much more on that unit. I kind of introduced it in the acid-base chapter, okay? And then, but the moles, let me just say this about the term the moles. To be able to communicate and to calculate from B to C, starting with grams, we have to find a common unit, and that common unit is the mole. Okay, that's how we get from grams of B. We take the grams of B, we will convert that to moles of B, and then from the balanced chemical equation, be able to convert that to moles of D based on the relationship of B and D. And once we know moles of D, then we will convert that moles of D to grams of D. The ultimate aspect is, if you recall in our chapter where we did conversion factors and ratios, and we set up this kind of a system, well, guess what? We're back to using that. We emphasize that particular system because, keeping track of our units, we are able to get from, extreme units from one unit to the other. If you recall that crazy example I did where I was trying to go, I think it was from bananas to dental hygiene students, okay? If we have conversion factors, we can convert from anything. And these coefficients are essentially a new ratio, and hence conversion factors to go from, in this case, B to D, okay? But we will get to that eventually. First steps first. So we're gonna need to learn to balance, not only identify the reactions, but then to balance. Now, what's involved with respect to balancing chemical reactions? Now, unfortunately, for some reactions, some of these types of reactions, it's a trial and error. It really is, unfortunately. However, not for all of them. We do have a systematic approach to balance the other types of reactions. But for the ones I'll be talking about, it's essentially just keeping track of your atoms. And the reactions are small enough that is not that, they're not that complicated as far as complexity. Okay, and a simple looking at keeping track of the elements as reactants products is fairly straightforward. Okay, and I'll go through some examples. Well, before we do anything, as always, we got to start someplace. Now, what's going to happen is you're going to be given a sentence that describes a reaction. Okay, from that sentence, we're going to convert it into a chemical reaction formula. We're going to convert these names of the compounds into formulas, and then write a reaction. And that's why we've been dealing, with as far as nomenclature is important, that we learn how to either, given the name, give the formula, or vice versa. All right. Now, the thing to remember with ionic compounds, in making ionic compounds, that we have to put enough of each. In other words, cation, anion, so they sum up to 0. Okay. And then as far as the name of the covalent compounds, we simply just follow the naming and the prefixes to give us the actual formula. All right. So again, once we were able to figure out the subscripts, if there is any in the compound, then we start balancing by playing with the coefficient and adjusting the coefficient so we have enough of each. For example, let's take this particular reaction here, all right? And it could be worded as follows, okay? Hydrogen in the presence of oxygen yields water, okay? So we know that hydrogen, symbol for hydrogen is H. We also know hydrogen is also one of the diatomics, okay? That's important, so refresh your memory with respect to the 7 diatomics. So hydrogen in the presence of oxygen or reacts with oxygen, that's a key word to tell you words to give you the plus symbol. With oxygen, again, we also know that that is also a diatomic species. Here you're given the physical states. So I didn't put them here, but they're given to you there. So we also have to learn, refresh your memory, I should say, about the physical states of the elements. Recall we had solid, liquid, and gas. Recall which elements are gases, which ones are diatomic, which ones are liquids. Remember, there's only 2 liquids, okay? And then the rest were solids, okay? And we need to refresh that so we know that what physical state we should put in, okay? Now, hydrogen in the presence of oxygen reacts to yield, to give, to yield, some key words there, which represents the arrow and water. So hopefully we all know the formula for water is H2O, okay? H2O. Sometimes it's, it could be something else other than H2O, and we got to figure out the formulas. So that is the general formula that we have there. Okay, as taken from the words I utilized to describe the reaction. Now we have to balance, okay? So we have the correct subscripts. The subscripts, once they're set, we don't change those. They're etched in stone, we leave the subscripts alone. It is the coefficients that we can adjust accordingly and change to any value that we need. So notice here that we have 2 hydrogens on the left-hand side and 2 oxygens on the reactant side, okay? With respect to hydrogens and oxygens, excuse me, I said hydrogens and oxygens, 2 on the reactant side. On the product side, we have 2 hydrogens in the form of water and 1 oxygen. So you can see that the hydrogens are okay as far as being balanced, but the oxygens are not. So what we do is we can add a 2 in front of H2O. What that does is now we have 2 oxygens, but what happens is hydrogen content kicked up. Now we got 4, no problem. We go back to the reaction side and we put a 2 in front of hydrogen. That then now balances our hydrogen. So we have a balanced chemical reaction, which tells us that 2 molecules of hydrogen gas plus 1 molecule of oxygen react to give us 2 molecules of water, okay? And that can be shown here by the formulas here. You can see here that we have a total of 4 hydrogens, okay? We have total of 2 oxygens. And then on the product side, we still have 4 hydrogens, but they're in the form of water. There's 1, 2, 3, and 4. And we have 2 oxygens in the form of water. So we have a balanced chemical reaction. They went from a the elemental state, hydrogen and oxygen, to a compound state. Okay. All right. Now that it's balanced, guess what we have? We have these new ratios. The relationship between hydrogen and oxygen is a 2-to-1 ratio. We can write in the form, this following form, 2H2 over 1H2, okay? Or we can invert it, 1 oxygen over 2H, okay? Remember when we were doing the conversion factors? Remember we had the 1 inch is equal to 2.54 centimeters as an example of one of them. And that was a ratio where we can write 1 inch on top, 2.54 centimeters in the bottom, or invert it where we had centimeters on top and 1 inch in the denominator, okay? Two ratios. Which one we use depend on the question and what units we needed to get rid of. And if we started with centimeters, and to get to inches, we will use the one on the left. Well, the same process would be utilized here. If we have a question, if we're given an oxygen, quantity of oxygen, and we need to calculate how much hydrogen, then we will use the one on the left. So you can see, let's say, for example, we have 10 molecules of oxygen, and we want to know how many molecules of hydrogen we need. Well, we will use the left. You can see that oxygens cancel. So 10 times 2 leaves us with 20 molecules of hydrogen gas. Okay, so those conversion factors come into play in our calculations. And that was the relationship between hydrogen and oxygen. But you also have a relationship between hydrogen and water, which is a 2-to-2 relationship. So 2 hydrogens over 2 waters, okay? Or 2 waters over 2 hydrogens, which is basically a 1-to-1. But, you know, keep the coefficients in there until you're comfortable with removing, because you can see 2 divided by 2 is 1. Okay, so that's another set. Okay, you have a third set, and that is between oxygen and water, where we have 1 oxygen over 2 waters. Okay, which we can write as follows, or 2 waters over 1 oxygen. Okay, and if you include the original ratios that we have 2 hydrogens over 1 oxygens, or 1 oxygens over 2 hydrogens. I'll try to keep them color coded here so you can see. We have a total of 6 ratios that we can utilize to get from one set of units or one set of molecules to the other, or compounds, whichever we're working with. Okay. And this one will get us to the point now that we can actually do a calculation between, let's say we need 100 grams of water for whatever reason, and we need to figure out how many grams of oxygen we utilize. So we use the relationship between water and oxygen, okay? Water and oxygen, which the ones are written in black. So one of those two. All right, but much more on that later on. Now, that's why it's important that we make sure that our reaction is balanced properly, because if we utilize the wrong ratio, obviously you can see, unless it's a 1-to-1, that if it's the wrong ratio, our number could be completely off. Okay. Now, the other thing about balancing these chemical reactions is, let's say for argument's sake, that instead of a 2, you come up with 4, 2, and 4. Okay. Now that process, those numbers still keep the reaction balanced, but as we do in mathematics, you want to use that number, bring it down to the lowest ratio. Okay, so you can see these coefficients here are all divisible by 2. Okay, so in doing that, then we are now balanced with the minimum number of coefficients necessary. So once you do that, check to see if it can reduce the terms, if you will, borrowing from mathematics, and you end up with that number there. Okay. So let's take some examples. Okay. Now, what we have here is a reaction that says that could stated as nitrogen reacts with hydrogen to yield ammonia. Remember that compound we worked with quite a bit with Lewis-Dot structures in the acid-base chapter. Okay, ammonia. So that's a reaction. Let me change. So let's figure out what we have. On the left side, we have 2 nitrogens and 2 hydrogens. Okay. On the product side, we have 1 nitrogen and 3 hydrogens. So you can see there that, let me rewrite this and keep it uniform. You can see that it's not balanced. So we have 2 nitrogens here and 2 hydrogens here. We're not balanced. Now, how to balance this? As a guideline, recall when we were putting formulas together, and we ended up, remember the point of adding enough, finding a common number. Recall we did, let's do an example. We had the aluminum ion and the oxide ion come together to form aluminum oxide. What do? We look for a common number, okay? Common number. So they ended up with having to have 2 aluminums to give us a total of +6, and we needed 3 oxides to give us a total of -6. So our formula came out to be aluminum subscript 2, oxide subscript 3. Okay, that's supposed to be a 3. Okay, but the point of all that was that we looked for a common number. We can use the same technique over here when we balance some reactions. If we look at let's just take a look at hydrogen, for example. We have 2 hydrogens on the left side, but 3 on the right side. So what if we look for a common number, which in this case happens to be 6 again? All right, so that means that if I put a 2 in front of ammonia, what that does is it kicks up my hydrogens to 6, and it kicks up my nitrogens to 2. Well, let's do the same on the other side. Okay, when I put 3 hydrogens, or 3 coefficients for hydrogen gas, well, that kicks up my hydrogens total to 6. And guess what? We have now a balanced chemical reaction. You know, in the beginning, when I'm learning to balance these, this really helped a lot when I started to put like a listing of the elements of each one and keep track of the numbers so I can make sure I end up with a balanced chemical equation. So I would write them all out and then start playing with the numbers and then updating them as I added a coefficient like I just showed you here. Okay, now we have a balanced chemical reaction. All right, so let's clear this up. There's a 2 there, there's a 3. And our relationship between reactants is a 1 to 3 scenario where I can write it as 1 nitrogen to 3 hydrogens. Okay, or invert it, 3 hydrogens to 1 nitrogen. Okay, but we also have the relationship between hydrogen and the product, which is a 2 to 3 relationship or ratio, and the relationship between nitrogen and the product, which is a 1 to 2. So again, we have a total of 6 ratios that we utilize and as needed. So, all right, let's do the next one. In this scenario, we have 2 hydrogens as reactants and 2 BRs. Okay. I call them BRs because in the reactants side, they're bromines, and the product side, they're bromides. So so there's no ambiguity, call them BRs. So I got 2 hydrogens on the left, 2, and on the right, I got 1 hydrogen and 1 BR. In this case, bromide, as you well know. Okay. So obviously we are not balanced there. Okay. So what can I do? Well, what if I put a 2 in front of HBr, or hydrobromic acid, okay? Or hydrogen bromide, because it's a gas. What if I put a 2 there? Well, that kicks up my hydrogen to 2 and my bromides to 2. Guess what? That simple coefficient balances the overall reaction. We have a balanced chemical reaction here. Okay. Now, quick word on naming here. HBr aqueous, AQ. When we take HBr and we run it through water, it dissociates as an acid. And so in this case, just like HCl, hydrochloric acid, this would be named hydrobromic acid. Okay. But when it's in the gas phase, it has not dissociated, it's still combined. So it's not really an acid because remember, definition of acid is a compound that produces a proton and a corresponding anion. So when it's in water, HBr will dissociate to form the proton. So its name is hydrobromic acid. And when it's gas, it has not dissociated, so it's called hydrogen bromide. Okay, hydrogen bromide. All right, just FYI, because you'll see a few times in the nomenclature exam, they'll give you examples of this, and just note the physical state. Are they talking about the gas, or are they talking about an aqueous system? Okay, and that's the difference between the two. Okay, so that's balance. All right, now we have the reaction of carbon monoxide in the presence of oxygen yields to give you carbon dioxide. And this particular process occurs in your vehicle because one of the products of our combustion of fuel is carbon monoxide. So it's doing what it can to kind of get rid of it and convert the carbon monoxide into carbon dioxide, which is not a poison. Okay, so what do we have here? We have 1 carbon and 3 oxygens on the reactant side, and we have 1 carbon and 2 oxygens on the product side. So Carbon's okay. What's not okay is the oxygen. Okay. So what could we do here? Well, there's a couple of possibilities. I would leave carbon alone and just maybe focus on the oxygens. Okay, on the reactant side, I got 3 oxygens, but they're separated, different forms. So what if I get them in a value that makes them, let's say, more divisible by 2, more divisible by an even number. So by adding a 2 there, doesn't that now give me 4 oxygens? Yeah, I got 2 in carbon monoxide, 2 is in form of oxygen, so that's good. But it also kicked up my carbons to 2. Okay, all right, no problem. If we go to the product side here and put a 2 in front of carbon dioxide, that kicks up my carbons to 2, so carbon's okay now. And that also kicks up my oxygens to 4. Okay, so it looks like oxygens. Okay, so everybody's balanced. I got 2 carbons on the left, 2 on the right, 4 oxygens total on the left, and 4 O's on the right. Okay, so we're balanced there. All right. So those are some examples where you're given the formula, and then all you got to do is just balance them. The samples there that we work with are fairly small. They're not very complicated. When I mean complicated, many reactants are coming together of big molecules. Now, so we can do a trial and error and play with numbers until we get a balance. And what that takes is we either start in the reactant side and add a coefficient, which generally makes us go to the product side, add a coefficient, and at times I may have to go back to the reactant side to add a coefficient or to update a coefficient. So I go back and forth whatever number of times I need. So I got my coefficients set up properly. And it does help to make a list, a grocery list, if you will, of your atoms, both on the reactant side and the product side, and keeping track of the number change as you add coefficients. And that will assist you quite a bit with respect to getting it to be finally balanced at the end. Okay. Now, that's not always the case for all of the other types of reactions. And I will give you some steps to go by when we get to the point of talking about the other types of reactions. So let's work on writing reactions with words, coming from words, which I just was doing for you when we're given the reaction. I converted that to words and remind you that those words could be converted to the reaction that you're given. Well, this is what we're doing here. Okay. Also remember the physical states: solid, liquid, gas. And if it's an aqueous system, and it will tell you it's an aqueous system, you put AQ. Okay. So refresh your memory, which elements were solids, which were liquids, and which were gases. So only 2 liquids, and I think there were about 12 gases, and the rest were solid. I did have a periodic table that was color-coded to show you who are the gases, who are the liquids, who are the solids, so you may go refresh your memory on that. Also remember which ones are diatomic. There's only 7. Have no fear of ice cold beverage. Okay. Remembering the diatomic. So if you're asked the question chlorine, if you're asked chlorine in the presence, which we're going to do chlorine here in a bit, chlorine in the presence of sodium, for example, well, you got to remember that chlorine is diatomic, so we would write the correct formula of Cl2, subscript 2. Okay. And so once we put the subscript, we put them together, those are etched in stone. It's the coefficient, which tells us how many molecules of each that we have of that compound or element, and we can change that coefficient as many times as we need. Okay, with respect to the subscripts, no, those are etched in stone. All right, so let's take a look at this one here. excuse me, is telling us that sodium reacts with chlorine to produce solid sodium chloride. So let's look at the key words here. It says sodium reacts with. Okay, so with sodium we have Na. We know that Na is for sodium. We are talking about the element. Okay, so the element sodium is a solid. Reacts with is the key words to tell you the plus, give you the plus symbol, okay? And here we have chlorine. So chlorine, the symbol for Cl is Cl for chlorine. And we know that it is diatomic, okay? And that it's a gas. To produce is the key word, reacts with, to produce, makes, things of that nature. It represents the reaction arrow. What follows after those keywords are the product. And here we know it tells us solid sodium chloride. Well, we need to write the proper formula. So here we're given the name of the compound. We got to write the formula. Recognize that it is ionic compound. Okay, so we write them in ion forms first before we put them together. So sodium we know is group 1A element. It is a +1 charge, +1 oxidation number. Chlorine belongs to group 7. Okay, it's a nonmetal. It will gain an electron, specifically 1, which gives it an oxidation number of a -1. All right, now we know all that. Now, hopefully, we are able to put them together in the proper ratio. So in this case, it's straightforward 1:1. Okay, 1:1. So the formula is NaCl, and then we're told it's a solid. Okay, so we have written the reaction as given by the words. Sodium reacts with chlorine to produce solid sodium chloride. Okay, sodium, a very reactive, very vigorous reactive metal, vigorously reacts with water. Chlorine, a poisonous gas, and they come together to produce something we can put in French fries, good old table salt. Okay. And all what happened was the transfer of electrons from the sodium to the chlorine. All right, now we need to balance it. So we have 1 sodium, 2 Cls, okay, and 1 sodium on the reactant side and 1 chloride on the product side. So our sodiums are okay, except the Cls are not. So what if I put a 2 in front of sodium chloride? Well, that kicks up my chlorides and my sodiums, okay? So now I got to go back to the reactant side. If I put a 2 here in front of sodium, that balances out my sodiums and my Cls. So we have a balanced chemical reaction. Okay, so let's write it out. So the first step was to write the formulas, okay, for the reactants and the products, and of course the oxidation state for all of them. Then we balance it. The question is, why don't we have? What do you guys think? Why wouldn't this formula be correct? Sodium Cl2. Why would that formula be incorrect? Maybe I'll ask that question. What do you guys think? Any ideas? Why would this formula be incorrect. Keep it in mind that the total ions should equal to 2. Okay, it's honest answer, not sure. Okay, but if we go back, we know that the chlorides each have a -1. Okay, so that means there's a total of -2. So if we go through the scenario, this states here that sodium under this type of formula suggests that it is a +2 ion. Okay, it can't be a +2, right? Because sodium, if you look at your periodic table, is in group 1A. It only has one valence electron. It's only going to lose one electron. Okay, and that's why we have the correct formula for sodium chloride is given up there, NaCl. Okay. All right. And then finally, to balance it, 2 sodiums plus 1 molecule of chlorine yields 2 molecules of sodium chloride. Okay. All right. And that's a balanced chemical reaction. Our coefficients are there. Everybody's balanced. That is our chemical reaction. Okay, here's another example. I have some examples of these reactions. These reactions that we're showing are very, very vigorous, extremely vigorous. During break, I'll see if I can dig up that. I think I forwarded it to or uploaded it to the course site, but if not, I'll see if I still have it, and I'll go ahead and upload it. But there's a file that shows all of these reactions, and you can show you how vigorous they can be. Okay, well, let's look at the next one. We have aluminum, which is Al. Okay, we're still dealing with the element. It's a solid. Reacts with, all right, so that's our plus bromine. Okay, bromine, which we know is diatomic, to produce solid aluminum bromide. Okay, so again, like the previous one, we have a ionic compound as a product. So what we got to do is first write them in ionic form to make sure we put them together correctly with the right number of cations and anions. Well, we know that aluminum is in group 3A. So when it becomes a metal, it has an oxidation number of A+3. And like bromide, like chloride, bromide has a -1. Okay, it's in group 7. When it becomes an ion, it will have gained 1 electron and have a net -1 charge. So those are our ions for aluminum bromide. And you can see that we need 3 of the bromides to cancel the positive 3 of aluminum. So our formula, okay, to produce is our signal word for the arrow, reaction arrow. And then we have aluminum bromide, solid. Okay. And that is our reaction. Now, once we got that, think about how we're going to balance it. As the example I did in the previous, we used a common number. Guess what? Looks like we have the same setup here. Let's set up my little grocery list of elements. We got 1 aluminum, 2 bromides, BRs, and product side 1 aluminum and 3 BRs. Okay, so we're not balanced. Aluminums are good, but we're not good with the BRs. So, but we do have 2 dissimilar numbers that we can find a common number. And so 6 again would be a common number. So if we put a 3 in front of bromine, that gives us a total of 6 BRs. And if we put a 2 in front of aluminum bromide, that kicks up the BRs to 6, but that also kicks up our aluminum to 2. Okay. So that means that we simply put a 2 in front of Al, aluminum, and we are balanced. Okay. And so we have balanced chemical reaction of 2 aluminums require 3 bromines to yield 2 molecules of aluminum bromide. Okay. And everybody is happy, everybody's balanced. There's the reaction we just wrote. I forgot the physical state, I believe, but the bromine is a liquid, one of the 2 liquids. Anybody know what the other liquid is of the elements? Good. Of 118 elements, 2 of them are liquids. One of them is bromine. Which one is the other? Do you guys remember? Let's see. Good. It's actually mercury, and it's correct. All right. And then we put the physical states. Okay, and we balance it up. Okay. And now you can see the ratio, in this case, between reactants is not a straightforward 1-to-1 or a 1-to-2 or anything like that. It is a 2-to-3 scenario. And so this ratio is 2 aluminum to 3 bromines, written in that form, or inverted, 3 bromines to 2 aluminums. Okay. The ratio between aluminum and aluminum bromide is a 2-to-2, okay, or 1-to-1, okay. And from bromine to aluminum bromide is a 3-to-2. 3-to-2. So those coefficients will be important, will be very important when it comes to doing calculations. For example, let's do a quick what if scenario. If let me clear this up. Okay. If I have 3 molecules of aluminum, how many molecules of bromine do I need is the question, okay? So as we were doing the problems back there where we did the conversion factors, we write down what we are given, right? So I have 3 aluminum, and then I write down what I'm looking for. I'm looking for Br2, bromines, okay? Given that I'm starting off with 3 aluminums. So I know I'm gonna have a conversion factor. Our relationship is between the bromine and the aluminum. So I'm gonna have a conversion factor, which is based on the ratio in that reaction we just did here. So I know that aluminum's in the denominator and bromine's in the numerator. Okay, I know that because I want my aluminums to cancel out. And I want to maintain unit-wise the bromine because that's what I'm looking for. I also know based on the coefficients that it is 3 bromines to 2 aluminums. Okay. Well, hold on 1 second. All right, so that's my setup. So if I do the math, I get 9.5, it's about 4.5 bromine. So if I start off with 3 aluminums, I'm going to need about 4.5 molecules of bromine to react. Now I'm saying molecules, but eventually instead of 3 aluminums, I could say 3 grams. And from 3 grams, I need to calculate how many grams of bromine I need, okay? But the point of that scenario I just did was to show you again how we set it up, like we did back when we had that second chapter, or 3rd chapter, I forget now, where we were converting units, converting factors from one to the other, okay? Okay, now you first write the reactions with proper formulas, and then once you've done it, you don't change the subscripts, then you just balance them by adding coefficients. Okay, and then we end up recognizing the reaction ratios that we may need to use in future calculations. All right, here's a reaction. Everything up to date has been ionic compounds. This is an example of covalent compounds. Okay, so we have phosphorus, which we know is P, reacting with, is our signal for plus, oxygen, O2. So phosphorus is a solid, and oxygen obviously is a gas. Okay. To make, okay, is the key word for the reaction arrow. Okay. And there's the product, diphosphorus pentoxide. All right. So here we first write the parent formula, which is phosphorus and oxide. And then we go back and put in the prefixes. So it's di, phosphorus, and penta, which is 5. So we got P2O5 solid. Okay. All right. So we have the reaction written down as written. Okay, or at least in the form of formulas, we have written down the formulas as it is written in words. Okay, now we're going to balance it. And guess what? Just like we had the previous example where we had the similar quantity, here we have two. Let's write this down. We got 1 phosphorus, 2 oxygens, and then 2 phosphorus and 5 oxygens. Okay. All right. Now, as a recommendation, when you have a reaction, when you find the element all by itself, like phosphorus, I'll save that guy for last. Okay. Work on the other element, in this case, oxygen. And notice that we have a 2 and a 5. So like we did before with that 2 to 3 relationship, we find a common number here, which happens to be 10. Okay, so if I put a 5 in front of oxygen, that kicks up my oxygens to 10. Okay, and if I put a 2 in front of diphosphorus pentoxide, that also kicks up my oxygens to 10, but it kicks up my phosphorus to 4. Okay, so far so good. And now all I got to do is put a 4 in front of phosphorus, and we are balanced. 4 phosphorus, 10 oxygens on both sides. Okay, and our ratio here is 4 phosphorus per 10 oxygens are required to create two molecules of diphosphorus pentoxide. Okay, so here's the formula. There are the physical states, and then we balance it out. So it's a 4 to 5 ratio. Okay, between reactants, a 4 to 2 between 4 to 5 between reactants of phosphorus and oxygen. Between phosphorus and the product, that is a 4 to 2 ratio, or a 2 to 1, but keep it in the numbers as given. And in between oxygen and the product, it is a 5 to 2 ratio. Okay, so those are the ratios that we may need depending on the questions asked about that particular reaction. All right, now, this type of reaction has a specific name, but I'm going to go ahead and work it through here, and you can try this at home, but it's given to you. It has a particular type of reaction, a name to it. We'll get to it in detail here in a bit, but let's break it down. So it looks very complicated, but like I emphasize about any type of chemistry that's given to you that seems complicated, and it may be, but I think for any type of complicated question or problem that you need to solve, you break it down, okay? Break it down into the pieces, okay? So what they're doing here is telling you this. Said, write and balance this aqueous reaction. So we know that everything's in the aqueous system, soluble in water. So we take a nickel 3 sulfate plus, that's our signal for the plus, or the plus symbol, lead 2 nitrate produces nickel 3 nitrate and solid lead 2 sulfate. And so first of all, you can see here where we have variable oxidation number metals. They're given to you in the form, the number, what oxidation stage are given you by the Roman numerals, but we got to put them together, okay, in the right ratio before we can write the reaction. So let's put them together first. Let me clear this up, and we'll start off with nickel sulfate, okay? All right, nickel sulfate. So nickel 3 tells us that we are working with Ni plus 3, okay? The sulfate, if you don't recall, is a polyatomic ion that you can go to the periodic table in the bottom left corner and look up, and you'll see that it's a SO4 negative 2, okay? So we're going to put these together in the proper ratio, okay, so that they are neutral. So we have dissimilar numbers, so we find a common number, which in this case is 6. So I need 2 nickels and 3 sulfates. Okay? So our formula becomes Ni2 parentheses SO4 subscript 3. And it is aqueous, okay? AQ. Plus is our symbol plus. All right, let us do the next one. I'm going to color code it, and this is lead nitrate. So we're using lead Pb plus 2. And the nitrate is, again, look at polyatomic ion. Look it up in the polyatomic ion table. It's NO3, negative charge for the polyatomic ion. So we need 2 nitrates for every lead plus 2. So we got Pb, okay, parentheses 2. Produces is our keyword for arrow. All right, now let's try different color. So the next one we're going to do is nickel nitrate. So nickel 3, we still maintain nickel 3, so it's a nickel Ni plus 3. The nitrate is NO3 negative. That means we need 3 nitrates for every nickel plus 3. So we got Ni parentheses NO3 subscript 3. Okay. And is our keyword for a symbol plus, the plus symbol. And let me change this to this color. And solid lead 2. So lead 2 is still Pb plus 2, and then sulfate SO4 negative 2. So in this case, we can put them together as a 1-to-1. So we have PbSO4, and it is a solid. Okay? Everything else is aqueous. So now I have written all the products and reactants in their proper numbers. That's the reaction, okay? Now we're gonna make sure we're balancing. You might think, oh my God, there's so many elements here. Now, when you're hit with a lot of polyatomic ions, to the best recommendation is to follow the polyatomic ions to balance them. Balance them as a whole. Remember, we talk about these polyatomic ions are treated as a unit. Okay, we do the same thing here. Treat it as a unit, we can balance them out as a unit. So let's look at the nitrates. Okay, in this scenario, I got 2 nitrates here, 3 over here. Okay, the other aspect is sulfates. I got 3 sulfates here and 1 over here. Okay? Don't worry about the metals. The metals will fall in place. Okay, just follow the polyatomic ions. So I'm going to follow the nitrates. So I got a 2 to 3 disparity. Like we've been doing before, why can't we find a common number, which is in this case 6? So that means that I'm going to need 3 lead nitrates and 2 nickel nitrates. So I can put a 3 in front of lead nitrate and a 2 in front of nickel nitrate. And that balances up my nitrates. Okay. I got 6 nitrates and 6 nitrates on both sides. Now that kicks up my nickels and my lead, but let's not worry about that right now. Let's go look at the sulfates. Okay. We had 3 sulfates on the reactant side, but only 1 on the product side. So what if I put a 3 in front of lead sulfate? Now my sulfates are balanced. Okay. I got 3 sulfates on the left, 3 on the right. I got 6 nitrates on the left, 6 on the right. So the polyatomic ions are themselves balanced out if we treat them as a whole, instead of having to count every sulfur, every oxygen. Just treat them as a unit, okay? All right, now, with that being said, let's take a look and see how our leads are, what happened to our leads. Well, we had 2 nickels here to begin with. And guess what? We got 2 nickels in the product side. Okay, so they're balanced. I have 3 leads on the reactant side. Guess what? I got 3 leads on the product side. So by default, the metals just fell into place and themselves got balance. And so we have a balanced chemical reaction that says 1 nickel 3 sulfate requires 3 lead 2 nitrates to yield 2 molecules of nickel nitrate and 3 molecules of lead sulfate. Okay, so let me rehash this type of reaction. This is a very specific reaction. Notice in the products, we only had 1 solid. And that's an indication of a positive reaction. Everything else is AQ, aqueous, soluble in water, okay, AQ. And so to rehash everything here is we're given this complicated reaction, okay, no problem. Let's simplify it. Take each molecule, each compound separately, write the proper formula by first breaking them up into the ions, like we did up here, to write the correct formula, okay? All right, once we did that for everything, then we looked at the polyatomic ion table, polyatomic ions, and we followed that. We figured out how to balance those out as a unit, okay? And we added coefficients. In this case, we had a dissimilar number. We started with the nitrates, but I could have started with the sulfates. That would have been fine. I started with the nitrates. I had 2 nitrates on the left, 3 on the right. Like we've done before, I find a common number. In this case, it's 6. So that means that I needed 3 lead nitrates and 2 nickel nitrates. So I put my coefficients 3 and 2 in front of the molecule. Okay. Next, I went and took care of the sulfates, balanced them out. Okay. So I needed a 3 because I had 3 sulfates on the left, and I needed 3 on the right. So I put a 3 in front of the lead sulfate, and that balanced all the polyatomic ions. Then I went back and checked my metals, and by default, they all came in, they all balanced out. Okay. Let me clear up my mess here. I try to color code it so you can see how I went through each one. Okay. All right. So there are the balanced chemical reaction. Okay. Notice in the products, okay, one of them is soluble in water, the other one is not. That is driven by the solubility rules. Okay. And when you have, if you look at the reactants, all they did was exchange partners. Okay. The sulfates got together with the lead to form lead sulfate, and the nickel got together with the nitrates to form nickel nitrate. So there was exchange of partners. Now, when you look at the product side, based on the solubility rules at the 2 products, we find that nickel nitrate is soluble. So we put AQ. So they remain in solution 100%. Because lead sulfate, based on the solubility rules, is insoluble, that precipitated and became a solid material that fell to the bottom of the beaker if you're working with a beaker. Okay, so that indicates a positive reaction. We call this, an example is a double displacement reaction. Okay, for double displacement reactions, a positive reaction is when one of the new reactants, one of the new products based on the solubility rules is insoluble and it precipitates. That indicates a positive reaction. If both of the new products are still soluble by the rules of the solubility rules, then there's no reaction. Okay. And that's how we can determine if a reaction, a double displacement reaction occurred, if one of the products is insoluble in water. And all what happened here is the partners, if you will, exchanged partners, if you will. So nickel and lead got together to make nickel nitrate, lead and sulfate got together. And that's just by the chance of them, because both of them, notice the reactants, both of them are soluble. So we got 2 clear solutions, okay? And when we put them together, they're still insoluble until they, they're bouncing around in there until the new partners just by chance get together. And when they do that, they're insoluble and they precipitate. Okay, all right. Okay, so a double displacement reaction. Driven by the solubility. So that brings us to the 6 types, okay? So we're gonna give them to you, in general terms using the letters A, B, okay? But along the line, the letter M represents a metal, okay? So A and B are, in this case, elements. Combination reaction. That is a case when 2 elements, notice A and B, are just by themselves. 9 times out of 10, they are elements. Okay, they're all by themselves, be it monatomic or diatomic. They're elements. When they come together, they form a compound, AB. And if you think about it, A and B combined, combination reaction, get together and created a new compound. A fairly good example of this would be, let's say, let me change the color because I'm on. Good example of this would be the coming together reaction of hydrogen gas plus oxygen gas. I'm not going to balance it. I'm just giving you the general reaction. Reacts to form a compound, which is water. H2O, okay? Two elements coming together. A decomposition reaction is the opposite of the combination. A compound undergoes a decomposition. It breaks down to the elements. And a good example of this would be water again, where we can take water and undergo electrolysis. We zap it with some electricity and literally break it back into the elements. Okay, to break it back into the elements. A decomposition reaction. So it's not going to come back to products. We break it down. A combustion reaction, and I won't go there, but a decomposition reaction just breaks it back, breaks the compound back to the elements. All right. The next type is a combustion reaction. Okay. Now, for Chem 130, okay, there's a variety of different types of combustion reactions, but we're going to focus on specifically hydrocarbons. And hydrocarbons are those elements, compounds that are made up of nothing but hydrocarbons. Okay, are made up of nothing but carbon and hydrogen. X represents the subscript for carbon. The smallest hydrocarbon there is methane, where X is 1, and Y for hydrogen is 4. And from there, they go into all kinds of numbers, big, much bigger numbers, okay? But we're going to focus on the combustion of hydrocarbons. Now, for anything necessary to combust, we require oxygen. So oxygen is always a reactant, okay? So it could be worded that methane, write the reaction for the combustion of methane, or CH4, okay? Well, we know that you need oxygen, so oxygen has to be as a reactant. Now, we're going to assume that the combustion process is 100% efficient, which in reality it's not, but we're going to make that assumption for this type of exercise. And that being said, means that the combustion of the hydrocarbon only yields two products. One is carbon dioxide, and the other product is water. Okay, that's it. Yes, I understand your vehicle produces carbon monoxide, and that's only due to the fact that our vehicles are not very efficient in burning hydrocarbons. Okay, but we're going to assume 100% efficiency, also only the combustion of hydrocarbons, and therefore the only two products you will see will be carbon dioxide and water. So again, you may be asked the question of write the reaction for the combustion of methane. Methane being CH4. Okay, write the reaction for CH4. Well, recognize it's made up of nothing but carbon and hydrogen. Also know that you need oxygen, and the only two products that are created are carbon dioxide and water. So you just wrote the reaction for the combustion of a hydrocarbon. Okay. We're going to learn how to balance these first. And we have a little technique for balancing hydrocarbons. We got stepwise steps. All right, let me erase this. That is a combustion reaction. Next type is called an acid-base reaction. We had the whole chapter on this, okay? We have a Arrhenius acid, and that is any molecule that when it's any acid, I should say, any molecule that has a proton that will release a proton, that produces a proton, is an acid, and the base is any molecule which will produce a hydroxide ion. And remember, the net reaction, the actual what's happening is the proton plus the hydroxide react to give you water. They neutralized, okay? The acid and the base neutralize each other. And then you have the corresponding salt. M here represents a metal. So what's left is the M and the A coming together, okay, to form the corresponding ionic compound. So that is a acid-base reaction, aka neutralization reaction. That is what happens when you ingest Tums for little acid problem. If you got, heartburn or something, you are reducing the acid content in your stomach. Okay, a single replacement reaction. We're going to talk about this in more detail. Okay, if you look at this general reaction, you start off with a metal labeled here M, right? Metal. And you have another metal, but it is in ionic form. Okay, hence you have AX. So A is in ionic form. And what happens is there is an exchange of positions. The A, which had possibly a plus charge, now goes back to elemental form, okay? And M, which was elemental form, now goes into ionic form. See what happened? They exchange partners, much like the one we just talked about, where two partners exchange, two reactants exchange partners. Here, just the metals, okay? A good example of this that you may be aware of is called plating. If you want to do gold plating, chrome plating, any type of plating. And so you have the metal that you want to plate on the surface. The metal starts off in ionic form, and then it is transferred and converted to metal form and plated on a surface, like gold plating. The gold starts off as an ion, and then gets plated on some surface to give you gold on the surface, okay? So that is called a single replacement reaction. And then finally, the last one is a double replacement reaction, which is what we just went through. Now, the subscripts here are not saying how many metals there is. It should be up on top. It's just showing you have metal one, like we did lead and nickel, two different metals. That's all that's stating, okay? So metal one now exchanges partners and now becomes, instead of MX, becomes MY. And then M2Y becomes M2X, okay? What is driven here is the solubility rules. If the new products, one of them is insoluble, then you have a positive reaction. And just for argument's sake, we'll say the M2X is insoluble, so you have a positive reaction. Okay. If both products are insoluble, we have no reaction. But double replacement reaction. That's how it is. The exchange of partners here, both partners. Unlike the single replacement where you just exchange one of the partners. Okay, and we can actually for the single replacement reaction, we will use a table that's again in the product table that would allow us to determine whether a given reaction will go or no. Okay, and it has to do with the reactivity of the two different metals. Another way to say that is that for single replacement reaction is that the metal M in this scenario is a lot more stable, is an ionic form than A is. Okay. So even though A is an ionic form, the fact that another metal comes into play, and it is, when we compare the metals, it itself, M, is a lot more stable in ionic form, reaction proceeds. Okay. If A is a lot more stable in ionic form than M, then there's no reaction. So we have another scenario, a go, no go scenario. But we're going to go through some examples to figure it out. So be able to recognize the type of reaction that you are working with, okay? Using these general reactions here. Obviously, the combustion reaction is very specific. It's a hydrocarbon, okay? And the acid base, very specific. You have an acid and the base coming together. The other ones may not be as clear, but if you look at the combustion reaction, you're always beginning with two elements, okay? Be it single elements, be it diatomic elements. And for a combustion reaction, decomposition reaction, you always begin with a compound that breaks down back to the elements. Okay? And then if you look at the single replacement reaction, you will see that you always start off with a metal in elemental form and a metal in ionic form. Okay. And then the last one, no question here, you always will find that you're dealing with, the majority of the time, polyatomic ions. Okay. Polyatomic ions. All right. All right. So let's talk about a specific one. All right. So here we have a combination reaction. What do we have here? We have phosphorus in the presence of oxygen. So can you recognize that you're dealing with elements, okay? And when they come together, you form a compound. Combination reaction, okay? And then obviously it's balanced here by putting a 2 in front of oxygen, and phosphorus balances it out. Okay, so combination reaction. Oh, let me clear this up a little bit here. All right. Next one, a decomposition reaction. Okay, how do we recognize this? Well, first of all, you're starting off with a compound all by itself, and then look at the products. You break them apart, and you're creating the elements, okay? Iron 3 oxide will decompose to form iron and oxygen. Okay, iron and oxygen. And then we have it obviously balanced here. Next one, combustion reaction. Here, the question is, write the combustion reaction for propane. The formula for propane, the general formula, the way it's written, is three carbons and 8 hydrogens, okay? So we know we're given the formula for propane, C3H8. We know if it's going to burn, and this is an example of we have a space-filled structure here. We got 3 carbons there, and then we got the 3 hydrogens bonded to the outer edge carbons, and then 2 in the center carbon. Okay, but this is propane that is burning. We know to burn, To combust, you need oxygen. Okay. And the second thing I stated earlier was that the only two products we're going to work with is carbon dioxide and water. Okay, that's it. Now, to balance combustion reactions of hydrocarbons, we do is a systematic approach here. Step number one, we first balance the carbons. Okay, we balance the carbons first. So if you notice, we have 3 carbons on the reactant side, but only 1 in the form of carbon dioxide. So we balance the carbon first. We put a 3 in front of carbon dioxide. That takes care of carbons. Okay. Second, we balance the hydrogens. All right. We have 8 hydrogens on the left-hand side, but we only got 2 on the right side in the form of water. So what we do is we put a 4 in front of H2O. That balances up the hydrogens. And then finally, we balance the oxygens. All right, so on the right-hand side, we only got 2 oxygens on the reactant side. On the product side, we have 6 hydrogens coming from carbon dioxide and 4 in the form of water. We have a total of 10 oxygens on the reactant side. So don't forget to count everybody, okay? That's one of the errors that occurs, that you see oxygen only in one of the products, but there's also oxygen in another product. So we have a total of 10 oxygens, 6 in the form of carbon dioxide, 4 in the form of water. So we need to balance it. We just simply put a 5 in front of oxygen, and that balances up the oxygens. And so we can see we got 3 carbons on the left, 3 on the right, 8 hydrogens on the left, 8 on the right, 10 oxygens on the left, and 10 total on the right for the oxygens. So we have a balanced chemical reaction. For the combustion, in this case, propane. So now when you're cooking out this weekend, with propane, you know what you're creating, and carbon dioxide and water. Okay. And when it's burning, the water is vapor, so it goes into the atmosphere as long as carbon dioxide. All right, so there's the reaction, okay? And then we balance it, again, balance it by doing the carbons first, then the hydrogens, and then at the end, the oxygens. Always remember that oxygen is always a reactant, and the only 2 products that you're going to get is carbon dioxide and water. Okay. All right, so let's do one real quick. Let's do 1, 2, 3, 5. Okay, 6. So we got C5. Okay. Do the practice on this. Do the combustion of, double check, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Do the combustion of pentane. This is the name of pentane, which is C5H12. Okay. C5H12. All right, so we write down C5H12. Okay. What is always a reactant? Oxygen. Okay. And what are always the products? Carbon dioxide and water. Okay. All right, now, carbon first, hydrogen second, oxygen's last. All right, so we got to balance the carbons first. So I got 5 carbons on the left, but only 1 on the right. So if I put a 5 in front of carbon dioxide, my carbons are good to go. Okay. Now, next step is my hydrogens. I got a total of 12 on the left, but only 2 on the right in form of water. So if I put a 6 in front of H2O, that takes care of my hydrogens on both sides. Okay. Now finally my oxygens. I got 10 in the form of carbon dioxide and 6 in the form of water. And so I have a total of 16 oxygens. Well, when I got 16 oxygens, if I put an 8 in front of O2, okay, I'm going to have enough oxygens to have this balance. I got 16 oxygens on the left, 16 on the right, 5 carbons on the left, 5 on the right, 12 hydrogens on the left, 12 on the right. So I have a balanced chemical reaction. So I can see for pentane requires 8 molecules of oxygen. Okay, 8 molecules of oxygen. For propane, didn't require as much. So as a hydrocarbon content goes higher in size, it requires more oxygen to burn it. Okay, which then produces more water and more carbon dioxide. So two things are happening here, where by combustion hydrocarbons, we are burning up a lot of oxygen and we are generating a lot of carbon dioxide. A lot of carbon dioxide got no place to go. It goes up to the atmosphere, builds up concentration. It's not going to leave the earth. Gravity keeps it in here, but it's going to go up to the earth and basically act as a blanket. Okay. And what that does, it means that any heat that our sun gives to the earth, normally with gases not as high up there, the heat is displaced into space. But when we have a layer of other gases like carbon dioxide, that heat is reflected back into Earth, resulting in higher temperatures in the air. So anyway, FYI, just to tell you what's going on. A good example of that phenomena has occurred in my lifetime here. Growing up in Arizona as a kid, I remember, hot days, but in the evenings it would be very cool. And I lived in Tempe for a long period of time once I came back. And there's lots of times in the city that the temperature is, in the 90s, which is highly unusual. And that's because of all the heat we picked up during the day. And all the buildings have maintained that heat so it doesn't dissipate as readily as before and gets pretty warm. Anyway, that's a combustion reaction, okay? Acid-base reaction. Okay? We have an acid, we have a base, forms water and the corresponding salt. Excuse me. Okay. My apologies, my coffee went down the wrong way. Okay, now, how to balance these? my suggestion is when it comes to an acid-base reaction, follow the protons and the hydroxides. Okay, let's take a look at the reaction here. We had the hydrochloric acid, okay, which we recognize as the acid. And then we have barium hydroxide, okay? Barium hydroxide is the base. All right, so we know that the proton will react with the base to form the water. Now note here with barium hydroxide, there are two hydroxides. So the net reaction between the proton and the hydroxide is a 1-to-1. Okay, remember that. I need one proton and one hydroxide to give me one water. And so if I have 100 protons, well, then I need 100 hydroxides to neutralize those 100 protons, and that would give me 100 waters. If I have two hydroxides, I am going to need two protons to neutralize those two hydroxides. And in doing so, I'm going to create two waters, just like I stated here. I said 100 and 100 will give me 100 waters. Okay. Excuse me. So I got the waters and the acid, the proton, and the hydroxide taken care of. Now we're going to look at the corresponding salt, which comes from the metal of the base and the non-metal of the acid. So in this case, it is the barium chloride. So as we did before, first write them in ionic form. So barium has a +2 charge, and the chlorides have a -1 charge. I need two of them, two chlorides to balance out the +2 of barium. So its formula is BaCl2. Okay. All right. So look at this. The fact that I balance the protons and hydroxides and the water, by default, the corresponding base balances itself out. All right. So let's take a look at the hydrogens. Well, I have a total of 4 hydrogens here. 2 of them come from the acid, and 2 of them come from hydroxide. So I have 4 hydrogens, and there I have a total of 4 hydrogens in the form of water. So they're balanced. The oxygens, I have 2 oxygens in the form of hydroxide, and I have 2 oxygens in the form of water. So they're balanced. I got one barium, and I have 2 chlorides, voila, it's balanced. Okay. All right. I'll give you, I'm going to clear my mess here in a second. Let's work on the next one. All right. We have phosphoric acid, H3. Remember I stated, how do I know it's an acid? Well, 9 times out of 10, hydrogen is written first. Okay. So that's a good indication I'm dealing with an acid first. Not always the case, but pretty sure here with 130, that's an acid. That indicates an acid. Okay. So I got 3 protons coming from phosphoric acid. The calcium hydroxide, which is a base, I only got 2 coming. Okay. All right. So guess what? I have a dissimilar situation here, like we've been working with a 2-to-3 ratio, 2-to-5. Well, I gotta find a common number. Okay. I need a total of 6, the common number 6. So I need 2 phosphoric acids and 3 calcium hydroxides. In doing so, that gives me 6 protons okay, and 6 hydroxides, which when they react, guess what? It will give me 6 waters. Okay. Now I got to deal with the salt, which is calcium and phosphate. Well, I write them out first in ionic form. Calcium is a +2, and the phosphate will be a -3. Also a dissimilar process here, so I need 3 calciums and 2 phosphates. So the formula is calcium 3, parentheses PO4, subscript 2, okay? Now, if you look through this, you will see that by default, my calcium is balanced and my phosphates are balanced. I got 3 calciums here and 2 phosphates from phosphoric acid. My protons and my hydroxides are balanced because I followed the acid and the bases, and so my waters and oxygens are balanced in the form of water. So they're balanced. Okay. So let me clear up my mess here so you can see the reaction. So we got 2 there. There it is. 2 there, 3 there, and there you go. Okay. So with respect to an acid-base reaction, to balance them, follow the protons and the hydroxides. Get those balanced, and the corresponding salt, once you write them in ionic form, will balance themselves by default. Okay? All right. Now, single replacement reaction. This is the one where I explained that you see the general reaction here. You start off with a metal element, okay? And then it will react, if it's going to react, with another metal that's in ionic form. And basically they exchange position. So the M replaces the A in ionic form to give you MX as a new product. And the A, okay, now went back to elemental form. And for argument's sake, let's just say that M reacted with A chloride, okay? And so we exchange partners and you end up with A chloride plus, excuse me. You ended up with M chloride plus A. Okay. Now, we know that the chlorides have a -1. So that infers that A, in this state, whatever A is, would have a +1. Agree? Well, we should, because that's the case. We know that M is an elemental form. Okay. And so M has a 0 charge oxidation number because it's an element. Okay. And so let's break down M. M goes from a 0 state to, again, as a product, Cl still has a -1. That infers that M1 is a +1 charge. So it went from a 0 oxidation number to a +1 oxidation number. So it lost an electron. Okay, for the metal to go from 0 to a +1, it loses an electron. Okay, and that has a specific number, a name to it, and we're going to talk about that. Okay, now if we look at the A starts off with a +1 charge, right? Because it's in the form of a salt. But then when it exchange partners with M, it now goes to a elemental form with a 0 oxidation number. So, and what's happening here, there's an exchange of electrons. Now, the main point is this, that M is a lot more reactive than A, okay? Because M is a lot more stable in ionic form than A is. It's a relative. Now, yes, A is stable in ionic form, okay? But when you bring in another metal that's a lot more reactive, they will exchange places, because M in this scenario is a lot more stable, if you will, in ionic form. And that's why this reaction proceeded. If A was the converse of that, if A was a lot more stable and more reactive than M, then there wouldn't be any reaction if A is a lot more reactive. Okay. And how do we determine that reactivity? Well, we use a scale. Okay. And that scale is, let me zoom up here, is on the periodic table right above the solubility rules. Okay. It's a list of active metals. Okay. Let's go over this. Okay. This is a relative scale. It is relative to hydrogen, which you'll see there. Hydrogen is given right here. Get a different color. Okay, hydrogen. Okay. Now, the way you read this is the most reactive metal is lithium. Lithium is at the bottom of the scale. It is more reactive than potassium, more reactive than barium, et cetera, until we get all the way to the end of the scale where we got gold. Gold is the most unreactive metal there is. Yes, you can get gold to react, but it takes very vigorous, harsh conditions to get them to react. Gold is called the noble metal because it's so unreactive. Okay. In fact, gold is so unreactive that it doesn't tarnish or change color after it's been buried for thousands of years underground. It's so unreactive, it stays just as luster and shiny as the day it was buried. Okay. So lithium more reactive than potassium, et cetera, et cetera. Hydrogen is what this scale is relative to. Okay. All right. Now, the metals that are listed in bold, that's going from lithium to sodium. These metals are so reactive that they, in the presence of water, spontaneously react just in water itself. And so those metals, which I'm just going to label as MX, okay, to represent lithium through sodium, when they react with water, they produce MX hydroxide plus hydrogen. And that's why they explode in water, because when they react with water, they will generate hydrogen gas and a lot of heat, and then boom, ignite the hydrogen, and it gives you a little bang. Okay. But then after everything's done and you check the pH, you'll find it to be alkaline because they produce a metal hydroxide compound. Okay. But that is only true for those under lithium through sodium, very reactive. The rest of them, starting from mercury up to lead, they require a little bit more vigorous conditions. I'm going to call those MY. Okay. They actually require like an acid solution, like HCl, hydrochloric acid. And when they do react, they will react and also produce hydrogen gas and the metal white chloride in this case, metal chloride. So it would be like aluminum chloride, manganese chloride, zinc chloride, this example. But it requires acid conditions to get those to react. After that, copper and gold, for all intents and purposes, they won't react at all. Okay, not at all, which is good for copper because copper is a good metal for piping in your house, for piping on water. You don't want copper to be reacting with water. But nowadays, all that piping is being converted to plastic, so not too much copper piping out there anymore, at least in the new housing. All right, so that's what's happening here. Now, let me clear up my mess here. When we look at a reaction, we find their position of the metals, find their position relative to each other, and determine which of the two metals are most reactive. Okay. All right. So let's go back. And that's going to tell us whether a reaction will proceed. So the metals that are most reactive, they have to go into ionic form, okay? And if they're more reactive than the other metal, they will get a positive reaction, okay? If they're not more reactive than the other metal, there's going to be no reaction. If the metal that you're looking at is most reactive and already in ionic form, you get no reaction. Okay, I'll simplify that here in a bit. Okay, we'll use the activity series, and this is an explanation of the activity series. That the ones that are highlighted here in white are the ones that are very reactive, react violently with water. Whereas the ones through magnesium to lead actually require more acid conditions for them to react, okay? So the most active metal wants to be a cation, okay? And their drive, like lithium, is always the most reactive metal. And if it's not in ionic form, it is in elemental form, it's going to exchange partners with whomever is reacting with. Okay, and least reactive, they want to just remain in elemental form. All right. So steps in writing a single replacement reaction. Okay, we checked the activity series, determine which is the most reactive metal. If the most reactive metal is already a compound, already in ionic form, there's no reaction. If it is not, then we just simply exchange the partners. Okay. And of course, we make sure we write the correct formula, charge, and so forth. Okay. And of course, we have the states to work with. All right. And then we balance the equation like we've been doing. All right. Let's take a look at this one here. Okay. Step number 1. We're going to compare, regardless of whether they're in ionic form or not. We're just looking at the metals. We got zinc here and we have sodium. Okay. So we go to the activity series and identify where they're at relative to each other. Here's sodium and here's zinc. So what we determine, number 1, is that sodium is more reactive than zinc. Okay. Now, that being said, is sodium in ionic form? Okay. Is it an ionic compound? Well, it's not. The reaction shows that it is in elemental form. So what's going to happen is they're going to exchange partners. So we've got zinc nitrate, okay, plus sodium. The zinc and the sodium are going to, if the answer is no, we got a positive reaction. In this case, the answer is no, so we're going to have an exchange. So we're going to end up with zinc. Zinc now goes from ionic form into elemental form. And then sodium is going to go into ionic form. So we write the ions like we've been doing. We know the nitrates are a -1. And so the formula for sodium nitrate is NaNO3. Okay. All right. So now we balance. Well, we've got 2 nitrates here, only 1 here. So we put a 2 in front of sodium nitrate. That balances the nitrate. It kicks up the sodium. So we put a 2 in front of sodium. And that balances the sodium. The nitrates are balanced. The zinc is balanced. So we're good to go. Let me rehash this. Let me restate what we just did. Okay. Here's the reaction. Okay. What we did first is we compared the metals, zinc and sodium, right here on the activity series, determine which was more reactive. And the series tells us that sodium is more reactive than zinc. Then we asked the question, is the most reactive metal in ionic form? Well, no, it's not. It's in elemental form, which tells you that yes, it's going to be a positive reaction. We're going to exchange partners. If the most reactive metal was not, is in ionic form, then no reaction. I'll do a reverse. If you got sodium nitrate plus a zinc, the question, which is the reverse reaction, the question, would it react? You ask the same questions. Who's more reactive, sodium or zinc? Well, sodium is, okay? Is sodium in ionic form? Well, yes, it is, okay? So if the answer is yes, and or no reaction, so there'll be no reaction in this scenario, okay? But in the opposite scenario, yes, there is a positive reaction, because in this scenario, sodium element, the most reactive metal, is in elemental form, not in ionic form. So therefore, reaction proceeds. So, simple question to yourself. Find the most, not simple step to look through it. Find the most reactive metal, number 1. Number 2, is most reactive metal in ionic form? Answers no, positive reaction, exchange the metal's position, okay? Answers yes, no reaction. All right. All right, so we have the reaction here and we balanced it out. All right. Obviously, we wouldn't write it Na with 2 nitrates. Again, that infers that sodium is a +2, and it can't be a +2. Sodium is a group 1A element. There's only got 1 valence electron. So that formula wouldn't work, okay? All right, tell you what, let's take a quick break. It's 2 o'clock. Let's come back at 2:15. And we will continue. Okay. Let me go back to where we ended up. Okay. So in this particular example, we're taking strontium bromide in the presence of aluminum, and then being asked is, will this reaction proceed? Well, we have to first recognize that we have a ionic compound and with a ionic metal, and this compound is reacting with an element. So that we should suggest to you that you're working with a single replacement reaction, okay? That's how you're recognizing that. You got aluminum here in elemental form reacting with strontium bromide ionic compound. So that being the case, then we look at the activity series between the two metals, okay? Now, we're looking at it regardless of whether the metal's in elemental form or in ionic form. So we're just comparing strontium with aluminum. So we can see here, there's SR right there, and aluminum's right there. So that tells us that, number one, that strontium is more reactive than aluminum. Second question is strontium ionic form? Okay, and yes, it is. It is in the form of strontium bromide. Therefore, the answer here is yes, implies no reaction. So we have here NR, no reaction. Okay, because strontium is more reactive than aluminum, and strontium is already being more reactive, is already in the most stable state that it has to be, needs to be, which is the ionic state. If the reaction was reversed, okay, let's say we took SR in the presence of aluminum, and the question is, would that reaction proceed? Well, we go through the same process. Yes, we know that SR is more reactive than aluminum, so that's correct. And then number two, is SR in ionic form? Well, in this case, the answer is no, okay, which implies yes on reaction, okay? So then we will get an exchange. So strontium, what was I doing? Aluminum bromide. Somebody caught that. Strontium reacting with aluminum bromide. Okay, that's okay. Still, the answer is yes, strontium. Know that yes, there's a reaction proceeding because strontium is not in the most stable form. So there's an exchange of partners here. So aluminum will go into aluminum elemental, and then we put together SR, which is a +2, and BR minus is a -1. So we go SR, BR2, okay, for the reaction. So no reaction in this scenario because strontium, which is the most reactive metal, is already in ionic form. Positive reaction in this form because the most reactive metal is not in ionic form. Okay, see how that works? Let me clean up my mess here. So no reaction. So when you get a no reaction, that means that the opposite reaction would proceed. All right, how about this one? Now, this is a little bit more challenging, but not difficult. Why? Because let's look at our reference point, which was hydrogen. Okay, obviously the elemental form for hydrogen is H2. The ionic form for hydrogen is H plus and a K H plus, and it could be also water. Okay, depends on the conditions, but most of the time it's just H plus. So with that, we look at the next reaction, okay, which was aluminum and hydrochloric acid. So what we're comparing here is aluminum, okay, aluminum versus hydrogen, which is more reactive. So we go to the activity series, which is there, okay? We look for aluminum, which is right here, okay? And the hydrogen, which is right there. So that tells you that aluminum is a lot more reactive than hydrogen. Okay. So then question number 2, is aluminum in ionic form? Is aluminum ionic? And number 3 says no. So that implies yes for the reaction. Okay. Yes for the reaction. So aluminum, hydrogen, which is H plus, will go to H2. Okay. And then aluminum goes into ionic form. So we know that aluminum will have a +3 and the chlorides will have a -1. So we need 3 chlorides for every aluminum. So it's AlCl3. Okay. Excuse me. Is the reaction. So let me clear up my mess a little bit here and bring in the other part. So there's the reaction, which is, if you think about it, when I was telling you about the activity series, remember I said that this group here will react with an HX, an acid, to form the metal plus whatever it is, charge-wise, plus hydrogen gas, okay? The ones here react violently with water to form the metal hydroxide plus hydrogen gas, okay? And the ones over here, basically, essentially for us, no reaction, okay? They will react, but they require some very strong acids, or even combinations of nitric acid, sulfuric acid, high strength to get them to react. Okay, so with that being said there, and we know that we should get hydrogen gas, okay, and then the corresponding salt, in this case, aluminum chloride. And then we have aluminum chloride based on the solubility rules, show it to be soluble. So we got AQ, and then we balance it up. Okay. All right. So there are YouTube videos concerning these reactions, so do watch them. All right. And there are in the modules, you'll find them in there too. So, all right. So to kind of rehash the activity series, is the ask the question, which is the most reactive metal? And then after that, is the most reactive metal in salt form? And if the answer is yes, then there's no reaction. If it's not in salt form, then yes, you get a reaction, okay? And hydrogen, the salt form for hydrogen, the elemental form obviously is H2, but it's the proton, H plus. All right, now which brings us to the double replacement reaction, which is what we did earlier with the nickel and the lead sulfate and nitrate we did earlier, okay? In this scenario, you have 2 soluble reactants, AX and BY. They're put in, mixed together. The partners are exchanged. So now instead of AX, now you have AY. And then you have, instead of BY, you have BX, okay? Now, based on the solubility, in this example, the AY is classified as insoluble and therefore is solid. Therefore, we have a positive reaction, okay? If both products are soluble, then there's no reaction. Okay, we call this a precipitation reaction because a solid was formed. Okay, a precipitate was formed. All right, so if a solid forms based on the solubility rules, a reaction will occur. Okay. No solid based on solubility rules, no reaction. So we got to utilize the solubility rules in the periodic table handout. And we went over these before, but just to refresh your memory quickly, is we have two columns. Left column, which is the soluble column, okay? If these four cations are bonded to any anions, then it's soluble. The acetate, the nitrate, 2 and 3, regardless of what the cation is, it's classified as soluble. The halides, so chloride, bromide, and iodide, normally are soluble regardless of what cation is bonded to, with the exception of silver, mercury, and lead. Okay, silver, mercury, lead, then they are insoluble. Same is true with the sulfate. Normally, whatever cation the sulfate is bonded to is classified as soluble. The exception is when you have calcium, strontium, lead, silver, or barium. Those sulfates are classified as insoluble, and you get a precipitate. Okay, a precipitate. Now, when we look at the insoluble column, okay, if we look at the carbonate, the chromate, and the phosphate, normally, regardless of what they're bonded to, they are insoluble unless they are bonded to the big four, okay? So there's only 4 examples of carbonates that are soluble. Everything else is insoluble. Same is true for chromate, and same is true for phosphate, okay? The sulfides are also true, meaning that whatever is bonded to the sulfides, they're normally insoluble unless they are bonded to the big 4 again, and calcium, strontium, and barium. There's 7 examples of sulfides that are soluble. Everything else is insoluble. Hydroxides are very similar. If they're bonded to the 4, they're classified as soluble. Otherwise, they're insoluble. Or if they're bonded to calcium, barium, or strontium, makes them soluble. Okay? So using that information, we're able to determine whether a reaction for a double displacement reaction is a positive or negative. Okay. So the quick way to do this is to quickly look at the products. They're creating new products. You're going to exchange partners, so you get barium and sulfate, okay? And then magnesium and nitrate, okay? So if we look at the solubility table, if you see number 3, okay? Number 3 means that any nitrate, regardless of what it's bonded to, it is soluble. So magnesium nitrate, the new compound, would not be a positive reaction. So let's look at barium sulfate. Look at sulfates, which normally are number 5 here, normally are soluble, except, guess what? Barium sulfate. So barium sulfate is insoluble, so guess what here? We have a positive reaction. Okay? Now, to complete this reaction, the first thing we need to do is actually put everything into ionic form before we can put everything together, okay? Because that will help us with the products. And so we got barium with a +2, okay? And then we got the nitrates with a +(-1). So I got 2 nitrates, okay? Then we got the magnesium with a +2. and then we only got one sulfate. Okay, now, once we have that, we know how to put them together. So the new partners are going to be barium and sulfate. So, excuse me, it's a -2 right there. So the barium will combine with the sulfate, okay, to give us a barium sulfate. We combine as a 1-to-1. We know from the solubility rules that we're going to have an insoluble product, okay? Then the magnesium will combine with the nitrates. Since magnesium has a +2, falls right into place. Those are the two nitrates, so those very quickly, the formula will be Mg NO3 2, okay? So you see what I did here? I first put them into ionic form so I can combine, put them together, the new products in the correct ratio. And by default, they balance each other out. So I got one barium on the left, one on the right, two nitrates on the left, two nitrates on the right, one mag on the right, one mag on the left. Okay, so it is balanced. Okay, and we know that the nitrates, I did forget to follow up on the solubility of the nitrates. We know that all nitrates, regardless of what the metal is, are soluble. So we get an AQ there. So this is a positive reaction. We get a precipitate, okay? And so if we were to draw a diagram of a beaker with this, we would have the bulk of the material down at the bottom would be barium sulfate, okay? And yes, there would be a few ions of the barium sulfate in solution because it's a weak electrolyte. And then the bulk of the other material, the magnesium nitrate, I can put, maybe 5 nitrates, and maybe 5 magnesiums and 10 nitrates in solution. See, that's what we see. We'll see a few barium in solution, but the bulk will be magnesium nitrate ions. That's a 1, not 2. Okay. All right. All right, let's take a look at this one. And we can just write the ions first. So we got lead 2. I know it's lead 2 because I know every nitrate is a -1. There's 2 of them. So I got the 2 nitrates. Okay. And then I got Ki, which is a +1, and iodide, which is a -1. All right. Now, we change partners. So potassium nitrate, we know that nitrates are soluble. All nitrates are soluble. So that combination would not make it a positive reaction. Then we look at lead iodide. Okay. Iodide's right here, normally soluble, except when it's bonded to lead. And so therefore, we have a positive reaction. So lead iodide is insoluble. And so let's put them together. We got lead 2, okay? It's a +2 state, so we need 2 iodides. So I need to put together Pb, I2, and then potassium and the nitrate. Potassium, nitrate, okay? Once I did that, I can balance them out. I'm taking these out. Again, I put them in ionic form first, the reactants, so I can make sure I put them together in the right ratio for the products. And so I have follow the nitrates. I got 2 nitrates here. I only got 1 here. So if I put a 2 there, it takes care of my nitrates, but that does kick up my potassium. So if I put a 2 there and put potassium iodide, that takes care of potassium. And by default, takes care of my iodide and lead iodide. So we got solid and the AQ over here for nitrate. There you go. Okay. All right, let's take a look at this one. Okay. 2 aqueous solutions, reactants, good indication we're doing a double displacement. Okay. The fact that we got nitrate here automatically should tell you that regardless of what the new partner is, barium nitrate, it's going to be soluble. So that would indicate a positive reaction. So let's look at silver chloride. Well, we got the halides. Here's the chloride, normally insoluble, except when it's tied up with silver chloride. Okay. So that being put together, I put everybody in ionic form so I can make sure I put everything back together properly. Okay. Okay, so I'm going to put together the silver chloride. So it's a 1-to-1, so it's going to be silver chloride. It's going to be solid. And then the barium nitrate, I'm going to need 2 nitrates because the barium has a +2 charge. Okay. Having a +2 charge, the nitrates each have a -1, so I need 2. All right, again, to balance them, follow the polyatomic ions. I got 2 nitrates on the right. What if I put a 2 in front of silver nitrate? That would take care of my nitrates on both sides. It does kick up my silver, no problem. Put a 2 in front of silver chloride. That takes care of my silver. Now my chlorides are up 2, but that by default, not a problem because barium chloride contains 2 chlorides. So I have a balanced chemical reaction here. Let me, here we go. Okay. Balanced. All right, well, which brings us to, I kind of introduced the next subject matter. So just to rehash, 4 double displacement reactions, we utilize the solubility rules to determine whether a reaction proceeds. 4 single replacement reactions, we utilize the activity series. Let me briefly go back to the combustion reaction, okay? Normally, the combustion reaction is pretty straightforward. You end up with a number when it comes to oxygens that are divisible by 2, an even number, and you just take half of that number and put it in front of oxygen, okay? And there you go. But occasionally that's not the case, and you can observe this. So let's take an example of a hydrocarbon, combustion of a hydrocarbon. Let's make sure I get the right one here. So 2, 4, 6, 8, and 614. This is called C6H14. This is another hydrocarbon called hexane. Just solvent used for a number of things. So hexane, okay? Hydrocarbon made up of nothing but carbon and hydrogen. So this is might say, write the reaction for the combustion of hexane. Okay, here we go, given the formula. It will require oxygen, obviously, to combust. And the only 2 products are carbon dioxide plus water. Okay, no different than the other combustion reactions of hydrocarbons. Now, step number 1, as before, we balance the carbon. So we got 6 carbons on the left. If we put a 6 in front of carbon dioxide, that takes care of our carbons. Number 2, balance the hydrogens. We have 14 hydrogens on the left but only 2 on the right in the form of water. But if I put a 7 in front of H2O, that gives me 14 hydrogens. So my hydrogens are balanced, excuse me. Okay. And then finally, the last element is the oxygen. Well, on the right side, I have 12 coming from carbon dioxide and 7 coming from water. So that is a total of 19 oxygens. Do y'all see that? Okay. 19 hydrogens. So it's not a number that's easily divisible by 2. Okay, it's an odd number. Okay, but no problem. Okay, what we want is, notice oxygen is diatomic, obviously. So we only need half of the oxygen atoms in 19. So if I had 19 halves of oxygen, that will balance my oxygens, okay? And that will be okay, except those coefficients cannot be whole numbers. Excuse me, cannot be fractional numbers. They must be whole numbers. So what we do here to help us to get to the whole numbers, given that we need 19 oxygens, we put a 19 halves in front of O2. Now, how do we get rid of that 2? Well, I'm glad you asked. We do that by multiplying everybody by 2, okay? So 2 times 1, this is a coefficient of 1, means that we get 2 hexanes, okay? 2 times 19 and a half, the 2's cancel. We end up with 19 oxygens, okay? And then 2 times 6 says we have 12 carbon dioxides. And then finally, 2 times 7 ends up with 14 waters. Okay. Now, check for yourself. You see you have a balanced chemical equation. You have 12 carbons on the left, 12 on the right. You have 2 times, you got 28 hydrogens on the left. You got 28 hydrogens on the right, okay? 19 times 2, isn't that 38 oxygens? Let me check my math. Right? And on this side, you have 24 oxygens coming from carbon dioxide and 14 coming from water, for a total of 38 oxygens. Okay, so and none of these coefficients, you are at the lowest terms, okay? You can't reduce them any further without getting into fractions, where we just came from with 19 and a half. All right, so that is a balanced chemical equation. So you use this little trick when you end up with an odd number of oxygens as a reactant, okay? And you take half of that odd number, put it in front of oxygen, and then multiply everybody by 2, and then you have a balanced chemical equation. All right, let me stop it there and make note here. And we ended up 28, slide 20. All right, let us stop it here.